Thank you, John. So our next speaker is Robert Ligon, who will be telling us about progress on the CHARA Michelson Array Pathfinder.
Thanks, John. Can everybody see everything and hear me?
Yeah, it's all good.
There we go. Hopefully that's good. I'm going to be talking about the CHARA Michelson Array Pathfinder. I'm Robert Ligon. I think Doug started off a good thing about the 2-meter Michelson CHARA array. We can think as the 1 meter as the Pathfinder to that. Just for some background, as was shown earlier, there's a topographical map of Mount Wilson, and CHARA is not in the flattest area, so expanding the facility is very difficult, even at shorter baselines, because of the terrain. And of course, if you want to go out very far, there's many obstacles to beyond a kilometer baselines, mainly with beam transport. So we had planned to try and do 3 locations of the 12 locations of the other one. And so on the map, you can see the first one will be next to the S3, which is next to our existing S1 and S2, which is where we do most of the engineering work for new stuff. And that baseline will give us some great short baseline ability just by hanging out there. But as Nick showed with enclosure design, we plan to be able to go to these other sites in red, S4 and on W3 to give us longer baselines. So there's a few major aspects to the project. The mobile telescope and enclosure. We need to have fiber zero pass stabilization, probably the most risky and important part of the project. Fiber transport, which will help number 2, and some control software. So the first part that we thought we'd get done, just because I have a super long lead time, was the mobile telescope. And we just had some simple high level requirements for it. Mainly that it has to be compatible with the current telescopes that we already have, so that we can interferometrically combine them. So phase delays between polarizations is critical for us, so that we can match it to what the other telescopes do. We'd like to have a 1 meter clear aperture. Also basic functionality, and we're going to be injecting H-band light, and so that should be pretty good. As far as general design possibilities, right, there's not many normal telescope design, right? It's usually a Cassegrain or a Ritchie-Chrétien. Of course, we use Mersenne and interferometry a lot, given what we do. And the last thing is, just to make sure the phase delays are good, which would be small angles and the coning materials, because the tertiary and the AOB photo are at 45 degrees, so we should use the same materials we use in our current telescopes. So after a lot of work, we purchased a Planeway PW1000 RC. It's off the shelf, so it saves us a lot in design and manufacturing, since they have been producing the 1000 CDK for a few years now. Matter of fact, in Georgetown, he has 3 of them. But the RC 700s are also around in many different facilities, so we feel confident that they'll be doing a pretty good job. The primary for it is f2.5, which is exactly the same as our current telescopes. We are going to be having bare aluminum coatings on the primary, secondary, tertiary, as in the current telescope, since we have a coating facility here. The output F number for the telescope will be 12.2. The secondary will have focus capabilities, but no tip tilt. So we'll add on a tip tilt system. And our expected delivery is fall of 2023, probably late fall of 2023. So to help with the mobile telescope itself, we did the preliminary design for the AOB bench. And as you've seen from the talks before, you know, we're going to be using a lot of the things that ourselves and our partners have learned working with CHARA. Mainly, we're going to use the same wavefront sensing system that we have at CHARA, and we'll also be using the LPL deformable mirror since we have a good experience with them. And it'll be 97 actuators, 11 across the diameter. And so the schematics that are over here on these on the boards are showing the AOB foe, which will be working as our fast tip tilt. Then we'll hit the acquisition camera, which is much closer to the front end than our current systems are. Then we'll have a collimating OEP. I apologize, I might not mention that the telescope be a Ritchie Chrétien. So we'll have to collimate again. And then the next set of optics, starting from the DM, will have a path very similar to the path of our current telescopes. And then, of course, the pick-off dichroic and the fiber and the wavefront sensor. Onto that, we'll go to the most important part of aspect of the project is the fiber zero pass stabilization, which has probably been worked on for decades now. And it's a good time to say congratulations to Aloha for their first fringes. They have a poster here that y'all can check out with all that great results. That's a great thing because success for them is actually success for us because we hope to partner with them on their stabilization system. And since all that takes a lot of time, we wanted to also work more. There have been some fiber experiments on stabilization at CHARA by Matt and also by Lehman, which was with Aloha. So we like to continue those and get a better understanding. This will help us with fiber transport and such like that to understand how good we have to deal with stabilizing the fibers. So in this photo here, we built up a simple spatial interferometer, basically Young's double slit. The apparatus up at the top, it just has two fibers right next to each other and a detector down there. And we just started on this and we just got fringes. So the goal is to be able to add more fiber in more different environmental situations to give us a better understanding on what we'll need to do. This will probably be ongoing for the whole project, obviously, and being modified as we go on with the systems that we get built. So for the fiber injection and collimation, these photos are what Aloha is using. On the left is actually the fiber injection at the telescope. And CHARA actually helped with a little bit of that. At least we gave the OEPs that are being used. They are not the best OEPs for our fiber injection needs, but we already have them built. So we will probably use them at the beginning because we have one on S1 and one on S2, which will be the first two telescopes that will interfere and also interfere with the mobile telescope. Given the small team that we have, we'll take the things that work, maybe not perfectly, but good, so we can concentrate on the things that we really need to concentrate on. On the right-hand side is the Aloha collimation side. Since they are going back into fibers for their instrument after the delay lines for us, we will be building a larger version of this so that we can go to Classic, which will be our first instrument for these experiments.
1 minute.
And so the next part on it is fiber transport, because stabilizing the fibers are much easier if the fibers themselves are stabilized, since they go very long distances. The two photos show actually what CHARA built for Aloha for sending their fibers to the S telescopes right now. And it's run along across the ground in a PVC pipe that was UV rated, but the sun still took its toll on it. And but it works, obviously, you know, and we would like to know if it was good enough, or should we go below ground, or actually it would really be nice, even though we think the stability might be a little bit less, if we could go between the transport plates, which already go to all the current telescopes. You know, we might need a little roof on top of it, just to block the sky for directly impacting the pipe to keep the stability. But we like to investigate all those ideas, because after stability, the transport is highly important. Trenching very deep is very costly, especially as we go out to our different sites that are further away. So we have all kinds of different things we're thinking about, even these little tiny concrete channeled trenches that we could put in, which might be a good medium between a trench and a above ground conduit. So, boy, I must have been a little bit fast. You guys can ask me a lot of questions. We got a 1 meter telescope. We've done the preliminary design for the adaptive optics. I'm sorry, I had a photo on that one. I had drawn in the some ideas I had for the calibration for the DM and the calibration for the wavefront sensor. As Matt had mentioned, you know, we noticed that there are issues, thermal issues, and we would like to try and minimize this in our design, because in the current telescopes, we use a reference actually in the lab, because the lab is quite stable. Since we're going to fibers, we won't see the lab. And so now we have to take a little bit more caution in having our calibration source, at least the wavefront sensor one. That will probably be the easiest. And if we can keep the wavefront sensor calibrated, then we can go to the DM and it'll have a calibration on the wavefront sensor side. Like I said, we're always like investigating which parts of the system is actually causing the issues that Matt had mentioned, so that we can incorporate them. As Nick showed, that we are doing concept designs for possible enclosures, and we're pretty close on that. And we're hoping to get that working. And we're working on the fiber transport areas. Mainly, we probably right now, as we show, we're going to start doing the fiber experiments for stability to get a better understanding for ourselves. And what do we have left? Lots, a lot of things left. We have to iron out the fiber metrology system and work out something with the Aloha team. We need to purchase the system. We have a lot of experience on the stability, as I mentioned. We want to install the fiber conduit, at least to the first spot, and the second spot down at S4 would be great as a start. And we like to finish the design of the AOB and get it purchased so that it will coincide, you know, 6 months before the delivery of the telescope, so we can test the system out before the telescope gets here. And of course, we want the enclosure delivered before the telescope gets here also. And then, of course, to connect all this, we need control software, which is also a good thing, because as Nick showed, he has been trying to upgrade a lot of the current telescopes to more modern electronics to make it easier for us. And we will use a lot of those ideas and systems he comes up with on the mobile telescope to make it easier to work on for us. And I think that's all I have. So I can have as many questions as you want.
We've only got about 3 minutes for questions, actually, but are there any questions? Okay. Rob, can you say what things you might be worried about with using commercial telescopes for this application, if anything?
There's a lot, probably. You know, the plane wave telescope's a little bit of a lighter telescope, you know, but it's, for us, it was, I think it's more that it wasn't the fiber experience, the most critical part of the project, right? And given the terrain of Mount Wilson, if we wanted to expand, we probably would need fibers. It's a risky part there, but it's, how we think we could expand. So the telescope is more of our Pathfinder. It should work pretty good. It's Planewave said it'll be diffraction limited, almost across down to an elevation of about 35 degrees, I believe, in the visible. So it's should be really well in HVAC. So, but since it is a lighter telescope, we always have to worry about things, right? Vibrations for interferometers is infamous. Matter of fact, I don't know if I ever been to an interferometer that did not have vibration problems. But we hope that we can use it in good seeing conditions, because we think in the initial times we'll need that anyway. Might not have totally answered your question, John, but maybe some of it.
Yep. Thank you. Right. Can we thank Robert again if there are no more questions?